Hello everybody. Today we are going to talk about tree data structures in Grasshopper. This is a very important topic as basically is an upgrade to normal lists that we have already examined in our previous session. What is a data tree? A data tree is actually, you can think about a data tree as a more complex set if compared to list, but you can simplify it by considering as a list of lists. For example, I'm going to draw a quick example here. So we know that a list is defined by a path, which is a single path for one single list. For example, if you take a panel component and you analyze a simple set of data like a list, then you will notice that there is a curly brackets here with an index or several indexes. It depends on how many steps were performed in Grasshopper to get to this list of data. So you might find this kind of path at the top right corner of your panel. And then there is a series of numbers here, which are the indices that gets to the last one. And then here you have the values or the items. So there is item 1, item 2, and so on. So this is a common representation for a simple list inside a panel, okay? Which is this tool, by the way. So if I grab this here, you will eventually see this kind of structure with the curly brackets and path here on the top right corner, and then you have the indices here, and then you have the items here listed in the wide area of the panel. What happens with a tree? You can think about a tree. Oops, there was an error with this pen while I grabbed the panel, but anyway, it doesn't matter. What happens with a tree structure? A tree structure can be seen as a list of lists where you have also a variation of the path. So if you take a curly bracket like the one that we have seen a while ago, so you will have these couple of indices here indicating the path to reach to this list, and in this list you will have the standard indices, like for example like 3. Then here the first list ends. You have item 1, item 2, and item 3, and item 4 inside the first list. And then the second list begins with this path here, where the first index stays the same and the second index starts to grow progressively. And then you will have eventually another list inside this tree with its own indices and its own items. So item 5, item 6, item 7, item 8, and so on. You can also have several other lists in this data structure. So this is a typical representation of a tree. Each time you see a different path, it means you are watching a branch of the tree. So this will be branch 0, and here we have branch 1. And each branch contains a set of data, which is basically a list. So a branch is actually a list of value. Okay, so you can think about this is the list 0, and then you have the list 1. So you can think of a tree as a list of lists. Okay, so this is actually indicating the index of the first list, and this is indicating the index of the second list. So 0, 1. It's like having items inside one list. Index number 0, index number 1, item 1, item 2. And then we have path number 0, list 1, and then path number 1, list 2. Okay, it's like having a list of lists. So this might eventually make it simpler to think about trees in Grasshopper if you consider them like separate lists inside one single data flow. Okay. What we're going to do with this data structure is analyze all of these components here, which are all the components from the set tree toolbar. There are some components that are easier than others. There are some components that are basically outdated. There are many utilities that have become more useful in Grasshopper than the oldest components. And this is, by the way, a lucky event, because there are some components that we are going to analyze that are way tricky to use. For example, the path mapper is the king of obsolete component that you can eventually skip during your standard workflow in Grasshopper. And but first, I'm going to go into our let's say analysis area. You see that here I have already placed something. What we're going to do this time is just grab the components and start from scratch once again. So, but first of all, I'm going to take, well, first this, which is the usual data set that we have been using also in the previous part of the course. And as you can see, this contains a list of values. And this is something that I am keeping, because it's very important to have valid item like these ones here, independently if it is text, numbers, or whatever. And here we have null items that it's important when we are going to use some tree utilities in a while. So that's why I am still working with this set of data here. And also I have grabbed this thing here, which is called param viewer. The param viewer, you don't find it in the tree section of the set toolbar. It is into param, utility, param viewer. Here it is. Okay, so this is a very important component, because it is basically a function that gives us an idea of the data structure inside one tree. And it also has another utility. We will take a look at this in a second when we will have a relevant tree. But we will be using this component several times during this analysis of the data trees, okay? Because it's absolutely useful when working with this kind of data structure. Even if in our toolbar the flattened tree and graph tree are not in the first position. As you can see, there is the clean tree first, but we are going to talk about the flattened and graphed tree first, because they are pretty important, and we cannot understand anything without these two components here. So what is flattened tree? What is graph tree? Let's see it in action. Okay. First, flattened tree makes sense only if we already have a tree, okay? But we don't have any tree actually. We are working with this data set here, which is a standard list. We can recognize it because there is a continuous double cable here. And here we only see one path, which identifies one single set of objects, okay? So here we have a typical representation of a list of values, okay? So first we need a tree, and if we want to convert, for example, this data set here, which is a standard list, into a tree, we must use this component here, which is called graph tree. So if I take this and I pass this data set to the graph tree, what this graph tree is using is creating the first data tree. We can see the difference now that we plug the cable into this panel. Okay, so the data tree you can recognize the data tree by basically three things. Of course, if you have a panel, it's evident. Okay, so we were saying, remember the scheme that we already draw here in this canvas. So you see that there is a path leading to an item. So this path represents the first list that contains one single object, one index 0, and then there is the item number 1. Okay, then there is second list number 1, and then there is index number 0 and item number 2 in our data set. So you can see that eventually, if I copy paste this panel and plug the list, you will see that value number 1, or index 0, is actually in list 0, position 0, while item number 2 is in list 1, that takes the place of index 1, and then inside the list 1 you have index 0 and item number 1 in our original list, and so on. Okay, so basically what the graph tree does when you plug a list inside this this input here, then it takes each single item coming in and send the item into a separate branch in the new tree. Okay, so it creates a tree by sending each item into a separate branch. This is, of course, this is an obvious way of recognizing a tree, because you see there are several paths here indicating several branches. Okay, so if you see this, then you are looking at a tree structure. Also, there is another graphic aspect that makes us understand that we are watching a data tree structure, which is the cable. So if you see this discontinuous cable, that you can consider like a double cable like this one, but discontinuous. So a double cable transfers a list. Here you have several lists running through this cable. That's eventually the graphic interpretation of this cable. So if you see a discontinuous cable, then you are looking at a data tree being transmitted from a component to another one via this discontinuous cable. But maybe this is only visible if you are plugging a cable starting from the output to another thing, be it a panel or whatever. But if you don't have a panel and you don't see any cable coming out from this component, and you want to double check whether the data structure is a tree or a list or one single item, then you hover with the mouse over the output, and you see that here, for example, we don't see we don't have any idea of the items contained inside this data set. For example, if I hover with a mouse over the data component here, I can see 18 locally defined values, and I see the values asterisk A, 0, 1, 2, 3, 4, asterisk B, and so on. Okay, but if I have a data tree, the only thing that I see is 18 locally defined values again, but then I see 0, 0, 0, 0, which is basically the path, and Grasshopper tells me that inside this path I will find only one item, n equal 1. It doesn't care about the item in this moment, okay? He's only telling us that we will find one item in the first branch, one item in the second branch, and so on. And it gives us an idea of the data structure in terms of branches. So you see that we have 3 indices of composing the branch that don't change. So the first 3 zeros stays constant. So you see that it's 0, 0, 0, 0, and then you have the second branch is 0, 0, 0, 1, and so on. So only the 4th index is changing, 0, 1, 2, 3, 4, 5, down to 17. So we have 18 branches because we had 18 values here. Okay, so remember that in Grasshopper, as in coding, when you have a list of things, the first item is always index number 0. So in this case, first branch has index, last changing index is 0. And the last changing index for the last branch is 17. So it means you have 18 branches in this data tree. Each branch contains one item, n equal 1 for all. Well, actually, we don't see the branches from 0, 0, 0, 10 to 0, 0, 0, 16. We don't see them because there are too many, and Grasshopper simply jumps to the last branch of the tree. How can we be sure of the data structure? We use the param viewer. Okay, so the param viewer is useful for this first operation, which is basically understanding the data structure of this tree. So if we plug a tree to the param viewer, we have this. The param viewer expands to visualize all the branches, and we see that we have all the varying index, the last index here from 0 to 17. Each branch contains only one item. Okay. Param viewer is a data structure visualizer, basically. If I plug a list here, he only says we have a data tree, basically, with one branch. And he says that the first branch, the only branch, has 3 indices, 0, 0, 0, and this branch contains 18 values. So as you can see, we were talking about considering a tree like a list of lists. But also a list can be considered as a tree with one single branch. And this here is the path of this branch. So if I take a panel and plug the list here, you see that this path is exactly the reported path here in the param viewer. Okay, and this is very important because in a second we are going to consider the composition of this path, because it's important for understanding how different data sets merge together or don't merge together. Okay, so it's important to consider the path and not only the items contained inside one data structure, be it a list or be it a tree. It doesn't matter. Okay, so branches, meaning the path, is as important as the values contained inside one single path, each path. Okay. The param viewer also has a graphic representation. So if you double click on the param viewer, you see that it changes its aspect and shows us a graphical representation of the data tree. Now, this is also important because it's a very intuitive way of understanding the complexity of the data tree. Remember that if you take a look at the text version of this param viewer, you would see that there is the path indicating the depth of the data structure of the data tree. So it means that in order to get to one item inside your tree, you have to start from, let's say, the root, which is 0, and then first branching, second branching, third branching. Okay, and then you find the values. So if you double click here, you will see that there is first branching, which is the first not green dot that you see here. Then there is second branching, third branching, and then you find all the items. So this is a 4 level tree, basically. This is the graphical representation of this aspect of the tree. Personally, I find this representation very interesting, very, let's say, aesthetic, of course, very pleasant to look at. But the most useful representation is, of course, this one. Okay, so I rely more on this to understand how a data tree works than on this thing here. So if you want, you can consider this representation, but keep in mind that, for example, these orange dots here, they represent the values contained inside the tree. Okay, now if you take a look at this representation, you will have no idea on how many values you can find inside one single branch. So it only says you have 4 levels inside your tree. So it's the first one here. You see these gray rings here. So this is the first level, second level, third level. At the fourth level, you will find the values. Okay. So this represents how many indices you will have in your path. But you have no idea on how many values you have inside each single path. It might be possible, for example, that one branch of one tree will contain one single value, and another branch will contain, I don't know, 1,000 values. You have no idea looking at this. But if you switch to the text value, the text representation, you will have an idea also on the content of each single branch. So you see that each branch contains one single value because here the param viewer is saying how many values are contained inside each single branch, not here, not in the graphical representation. So I would rely more on this representation than the graphic aspect of the param viewer. So this is how we create a tree. Well, actually, the graph tree not only takes a list and converts it into a data tree with one single item inside each single branch. It also adds a level to an existing tree. Okay. For example, well, I'm not going to comment this in this moment. We will talk about this later when we will have more complex trees. Okay. One way, well, no, let's do it now because it's actually it's based on something that we already seen when talking about the lists. Okay, so if you remember in the list group of components in the set toolbar, there was this partition list here. Okay, so if I take partition list and take this list and break the list into chunks, now size is by default set to 3 and 2. Okay, so what I'm doing here is creating a tree with 7 branches, and the first one contains 3 items, the second one contains 2 items, and so on, 3, 2, 3, 2, 3, 2, 3. This is coincidental. We have 18 values, and we are considering division like 3 and 2. So we have an even distribution of data inside these 7 branches. Okay. But this is coincidental. I can use, for example, a slider between 1 and, I don't know, 5, and copy paste it, and then I can use these values here as the, well, let's grab a param viewer actually. It's more useful. So what I'm getting here is a size of all the branches will be 1 because I have only 2 identical values which are 1. So this is just like grafting, of course. But if I take this and increase it to 2, I will have 1 branch with 2 items, 1 branch with 1 item. What I want to show you is that I have now 12 branches, each one with a different number of values. But if I switch to the graphic aspect, I don't see any information leading to the number of items that I have inside this branch here. Okay, so I have no preview on how many items I have here. So that's why I prefer this text representation. And we can change this, for example, and you see that if I select, for example, 2, 5, I have 2, 5, 2, 5, 2, 2, because there are not enough data to fill the sixth branch with the same amount of items as branch number 3 and 0. Sorry, and 1. Okay. Okay, so now we are creating a tree also with a component that is not contained inside the tree set of functions. Okay, so trees come up during the standard Grasshopper workflow for several reasons. Also using graphical functions, graphical components. So we will take a look at this in a while later on. So here we have this data tree with 6 branches, and each branch contains 2, 5, 2, 5, 2, 2. What happens if I graft this tree here? Okay, so if I plug the chunks inside this tree, now I am grafting an existing tree. I'm not using graft to create a tree. I'm using graft to further grafting existing branches. Okay, so if I take a param viewer and plug the result of grafting, we will have our 18 branches data tree. But this 18 branches data tree is different than grafting directly the original list. So for example, now we know how this partition list is splitting our list. I will only grab a graft tree and once again graft directly the original list. Okay, so I will take another param viewer and analyze the structure of the grafted list if compared to the graft tree applied to the partition list. So what we are doing here is creating two trees, with 18 branches, but with a different workflow. Okay, so the first data tree that we already created with a simple grafting of the original list, we already know that is basically a data tree with 18 branches containing one single value. But if we take a look at the second data tree coming from the partition list, first the partition list creates a tree, and this tree has only 6 branches from 0 to 5. Okay, so and we see that we are creating a data tree with 4 levels. Okay, when we graft this tree, we are grafting the items that are already contained inside one branch. So basically what we are seeing is that the 2 items contained into branch 0000 will separate inside 2 sub-branches of this branch here. Therefore, we will have 0000, which is the first branch, and then we will have 2 indices, 0 and 1, each corresponding to the 2 items contained inside the first branch. Then we will have branch number 0001 will split into 5 sub-branches. So we will have 0001, and last index will be 0, 1, 2, 3, and 4, and so on. So this is a different data structure. It's very different from this other one. So if we take a look, for example, at the graphical aspect, in this case, for example, it can be useful to take a look at the graphic aspect of this data tree. We will see that the first data tree is simpler because each branch represents an item and connects directly to the root. Okay, but if you take a look at this, you have 2 levels of splittings of our branches. So the first knot here, the first green dot, is actually the first splitting occurring, which is the 6 original branches. And then we will have the 2 items splitting into 2 sub-branches, and then 5 items, 2 items, 5 items, 2 and 2. Okay, so this tree here is absolutely more complex than this one. Okay, so you don't want to mess around with trees if you don't know exactly what you are doing, because also the data structure inside a tree is very important. The simpler the tree, the easier will be to work with this tree. But there are some occasions where you don't want to lose this complexity, because you don't want to lose the grouping by sub branches. Okay, so in case it's important for you to have this irregular or periodic division of items inside branches, you don't want to simplify this tree here. You want to maintain this kind of irregular splitting of the branches. Okay, so this is way more complex than this one, but sometimes it is necessary to keep this kind of complexity for data trees. So 2 data trees with 18 branches each, but very different in structure. Okay, so grafting, depending on if you are grafting a simple list or you're grafting an existing tree, it can have different consequences. What happens, for example, if I graft this tree? So we have 1 item per branch. We have 4 indices composing a path. If I graft once again this tree and plug it here, I am only adding an index, which is not changing, by the way. So I am adding a sub branching that has no meaning, because there is no splitting of the branches and we are adding no useful information. So when you see this kind of non-varying last position index, this is absolutely useless. Okay, and there is actually no reason for doing this. Also, once we have grafted this partition list and we have already reached 1 item per branch, independently from the data structure, which is more complex, if we further graft this tree here and take a look at the structure, we are also adding 1 useless non-changing index in the last position of the path. Okay, so basically when you get to 1 item per branch, there is no use in branching and keep on branching or adding levels or depth to our tree. Okay, it only adds complexity that it's useless, and it's a kind of complexity that the Grasshopper can easily remove, and we will talk about this later on. So just don't use graft if there is no need to do it. Okay, then we will discuss about the use of grafting in a regular Grasshopper workflow. So what happens when we also I will keep let's say I will keep trace of this different trees here. I will just maintain this this example that we made, because I think it's useful. Sorry. So I will copy paste each param viewer and leave the text representation together with the graphic representation of the tree. Also, the param viewer in the graphic representation, there is no point in leaving it so big. You can simply shrink it to the smallest possible size. So I will leave it like this in order to have an idea of the structure, or maybe a little bit bigger, just to have it like exactly like the other param viewer. And I will do the same with this. So I will copy it here and switch to the graphic aspect, and then I will take this one and copy it here and switch to the graphic representation. So like we already made with the first one. Okay, so we have this, and then we have also this. So we will have an idea. I will also shrink a little these param viewers, so we will have the possibility to organize the definition a little in a clearer way. Okay, so here's the example of grafting, graphed tree components. Okay, and the opposite of grafting is flattening a tree. So if I take flattened tree, now that we have trees, we can see how the flattened tree works. So for example, if I take the simple tree that we have created here by grafting the original list, and then I plug it into the flattened tree, and path, you see that path is set to 0. Okay, so it is curly bracket 0 curly bracket. What we have here as a result is that it's like cutting the tree, basically. Okay, so if we cut the tree, all the fruits basically that are actually divided into sub branches, they will all fall down to the ground. Okay, and the ground is represented by this path here. So if I flatten this tree here with 4 indices per path, and I flatten them to a path which is 0, what I will get is a list with this path as the floor, basically, and all the values contained inside one single list, which is basically the floor level of our tree. So flattening is like cutting the tree and having all the items at the same level, which is defined by the path. So for example, if I take a let's build a list. Okay, let's build well, no, we will do this later on. Okay, so just to have things clearer, I will go here inside the path input, and where it says set path, I will use a notation that we already know, because you see that the path is curly bracket, first index, semicolon, second index, semicolon, and so on. How many indices you want into this path. Okay, so if I go here in path and set path, here I can add semicolon, for example, 0. So if I do this, our floor will be 0 semicolon 0. So 0 0 there will be 2 indices per path. Okay, so here you define at what level is your ground when you cut the tree. So for example, I could say, for example, that I want to flatten this tree here that has these 4 levels. I want to flatten all these values here at the second level, which is what we are doing here. Okay, so if we grab a param viewer with a graphic representation, we will see that our items lie at the second level. While if I go here in path and set path and delete the second index, you see that there is only one level inside this list. This is the simplest data structure, okay, as a list of values. So here you can define the path of your list. I repeat, this is important because the path is important when you are blending or mixing data sets in Grasshopper. So it's important to have direct control over the path also when you have lists, not only when you have trees. Okay, so I will leave this like this, so we will have an idea. You will have an idea of what this flattened tree does. Also, I will do like this. So path is set to curly bracket 0 curly bracket. So I will extract parameter. So this will be a path, and then I will copy it, and here I will set the other path. So this will give us an idea of what happens when we have different path defined inside this input. Okay, so let me group this so we know what we were doing here. So flattening and grafting are two very basic operations, but they are fundamental when we are working with data trees. So let's jump to actually the first component in the set tree toolbar, which is this green tree. It is a very important command. It allows to actually get rid of any problematic data inside Grasshopper. It's actually I won't consider the invalid data. It's something that might come up during a regular Grasshopper workflow. From time to time you might notice that Grasshopper casts some invalid things around. So with this you can get rid of them by activating the Boolean toggle set it to true for remove invalid. But now let's take a look at how the clean tree component works. I am using the same data set that I have been using through the previous session. So we see that there is this list. It's a heterogeneous list of text and numbers and also null items. So what I'm going to do, I'm going to convert this list into a tree by grafting. So we know that this graph is actually generating a tree where each value here is occupying a branch. So if we take a look with the param viewer that we already know, we can see that there are 18 branches, each containing one item. And therefore we have this representation for our data tree. As we can see here, branches from 12 to 16 will contain null items. Okay, so if I go and leave these all to false, like I don't want to remove nulls, I don't want to remove invalid data, which we don't have by the way, and I don't want to remove empty. So actually this clean tree is doing nothing. So if I take a look at the panel here, after the clean tree, I see exactly the conversion from the list to this tree, and then nothing happens to this tree because clean tree is doing nothing. So we see that there are branches from 12 to 16 that contain null items. Okay, so what happens if I decide to remove nulls? I set this to true, and now I see that the panel just switched to a shorter version. You see that there are branches between 12 and 16, they are completely empty. And it's not a good idea to maintain empty branches in general, so you might want to get rid of them too. So you just activate the remove empty, and clean tree will also remove branches between 12 and 16 because they're actually empty because we deleted the nulls inside them. Okay, there are particular situations where you might want to avoid deleting the empty branches in case you are, for example, making this tree interact with another tree with the same structure. You might want data from each tree to combine inside the respective branches. So in this case, you might want to leave remove empty to false. We will discuss data interaction in a while. But in general, if you want to get rid of anything that might cause an improper behavior in Grasshopper, you might want to start with nulls and invalid, because these data, if are transmitted or propagated through the definition, they might cause some undecided behavior from some functions. And also you can remove empty branches in your tree by activating this Boolean toggle here. So this is how a clean tree works. By the way, it also works with lists, not necessarily tree. Remember that we can consider a list as a tree with one single branch. Actually, you can see that even one single list has its own path. So it's just like having a branch with one single, a tree with one single branch, sorry. So if I take this list here, copy paste it and move it here and plug it into tree, what I'm doing, I am removing null items. Of course, there is no meaning in removing empty branches because there are no branches in this list. There is only the main one. But remove nulls is actually deleting and removing the null items between 12 to 16. Okay, so you see that here you have no invalid or null items. So you can also work with lists when using the clean tree. Okay, just let's switch back to this, and I will leave this as it is. Now, of course, this the choice that we make here has consequences in terms of the tree structure. So, for example, if I take a param viewer and plug it here to the final result of this clean tree, you see that here, as I'm not removing the empty branches, I still see a data tree with 18 branches. I see that 12 to 16, they are empty branches. And if I remove empty, I have these 13 branches where I jump from 10, 11 to 17. So I have this new data tree where I, once again, the more important visualization method is the text version of the parent viewer, so you have a clear idea of what happened to this data tree through the clean tree command. Okay, so I will leave it like this, so there will be evidence of what we were doing. Okay, so now let's go to these other components here: prune tree, simplified tree, tree statistics, trim tree, and a flattened tree. They are more or less easy. We will go through the difficult things in a while. Prune tree, I'm going to create a different tree, because I cannot work with a tree with only one item per branch. You see that this tree actually is removing branches, but also only small branches. Okay, and with this minimum and maximum, you decide how many items are inside the branches that you want to delete. So this allows to eliminate those branches that contain few values, for example. Okay, so I'm going to use this method here, so I can work with a more complex tree where I have like this, where I have 2, 5, 2, 5, 2, 2. Okay, and let's say that I take this data here and I internalize this tree, so I have it available here at the bottom. Okay, so this is the tree that I want to clean and to prune. And as I am building a new definition here, I will just copy a panel here so we can see what's inside this tree. And also I would take a parent viewer so we know what's inside this tree. Okay, so this is our starting data set. Okay, and I want to prune this tree. Now what I want to do, I want to eliminate those branches that have, for example, you see that there is a minimum and maximum. You can remove, for example, branches. This is basically what branches you want to accept, not actually what you want to remove. So minimum value here is the minimum amount of data that a branch must contain in order to be kept. Okay, so for example, if I say I want to use 4 here, and I take a look with a parent viewer at the result, you see that all the branches that contain less than 4 items are being removed from the data set. Okay, so you see that only the branches with 5 items are being kept. Okay, so for example, if I delete this and I use a slider between 1 and 5 and plug it here, if I say I can accept the branches with at least 1 item inside, then also the branches with 2 items would be kept. Okay, if I set this to 2, nothing changes, but if this changes to 3, then branches containing only 2 values will disappear. Also, I can leave these to 2, and I can, for example, take another slider, copy paste this one, plug it to maximum. Okay, so I am considering that I will keep only branches that have at least 2 items inside and maximum 2 items inside. So you see that only the 4 branches with 2 items are being kept. The 2 branches with 5 items disappear because I cannot accept them because they have more than 2 items inside. So if I set these to 5, they are back again. Okay, so with this we can decide, for example, if we want to eliminate some specific branches from a data tree according to the amount of data that they contain. And so you can see clearly the difference between the input and the output of this workflow. Simplified tree, it's way easier than this. It's just something that alters the depth of the tree. So for example, let's once again take this tree as a reference. We already know it, so I won't be copying the parent viewer and the panel. So what this simplified tree is doing is actually eliminating all the indices in the path of the branches that simply overlap, but so basically they don't make any difference if they are if they are taken into account or not. For example, if I take a look at this tree here, you see that the first branch is 0, 0, 0, 0. Okay, then the second branch is 0, 0, 0, 1. Okay, and you see that only the last index is changing, but the first three indices are not changing at all. So what if I define a path just considering the changing index and not the indices that stay totally equal? Okay, so this is simplifying the tree. Okay, so if I take a look at with a panel to the result of this, you see that only the changing value has been kept in order to define the path of this tree. Of course, we are changing the depth of the data tree structure. So for example, if I take a param viewer, we know that this is the initial tree. This will be the final data tree. Nothing changes in terms of branching and in terms of amount of values inside each branch. But what changes is the structure. So you see that these branches start to appear from the third level on. So it's the fourth level that is actually branching. And here you see that you have no trunk basically in this data tree. Okay, you only have branches. So we are eliminating all the redundant steps that we need to get to the final branching of our tree. Okay, of course it has consequences. It is very useful when you want to create interaction between data trees, especially when you try to do some complex operation with data sets and something goes wrong. Probably is because you're not simplifying the trees, but we will see these in action in a while. And also keep in mind that, for example, all of these things that we are seeing, well, not all of them, but flattening and grafting, as well as simplifying a tree, are commands that are also contained inside the inputs and outputs of Grasshopper functions. Okay, so we will discuss this later on when we will be dealing with practical examples. Tree statistics is very easy. It just gives you the numbers which are that define basically the data structure of a tree. So you see that, for example, if I take a panel and plug the paths, you see that here we have the paths defining the branching of our tree. If I take another one and plug length, you see that this is the amount of items that I have inside each branch of my data tree. And then we have count, which is the number of branches that we have in our data tree. These are all very important information regarding the data tree that we are analyzing. Okay, because as we will see in a while, many of the components that we have here in the tree group allow performing some specific operations on data trees, but you must work with, for example, paths, okay, or branches, and it's not convenient actually to type or write down the path to specific data or data groups by hand. So here you have a quick way of accessing the paths of your existing data tree. Okay, so it's a very nice thing to have this tree statistics component available. Let me make some order. Okay, and then now let's go to the trim tree. You see that this is something that it's a very delicate operation. You see that there will be also another command that acts more or less like this one. We will talk about this later. Is the shift that we will see here is this one, shift paths, but we will discuss this later on. It's not exactly the same, but you might think of the two commands like something quite similar. Let's take our complex tree, which is well, actually maybe not this one. Maybe we should work with the grafted tree, which is this one. So I will take another data container and plug this complex tree here and internalize the data. Okay, and also I will, just because I'm here, I will copy paste this two param viewer, so I will bring them with us in the next definition. So let's take all of them, move them down, and what I want to do, I want to plug this new tree to our trim tree command. And now it asks the depth, and you see that depth is number of outermost branches to merge. Now the outermost branches that we have here, you must consider that, for example, we have this sub branching in this case. So for example, here we have the main branching that was occurring, which are these 1, 2, 3, 4, 5, and 6 main branches, and then we have sub branches which are 2, 5, 2, 5, 2, 2. Okay, so this is our structure, and you see that depth is actually asking for an integer value. Okay, so we must decide how many branching we want to affect with this trim tree. So if I set this to, for example, let's say from 0 to 2, and if I say 0, of course, in this case, let's copy paste this so we have it available here. So you see that in this case nothing changes, of course, because we are not affecting anything in our data tree with a 0 depth. But if I set this to 1, you see that now basically what's happening is that the first sub branching starting from the items is basically disappearing, and we are getting back to the original data tree that we already had here. So it is this one. Okay, so it's absolutely identical. 0, 0, 0, 0, change it up to 6 with this single branching here. And here we have the result in our case, 0, 0, 0, 0, ranging up to 6 with this single branching that happens at the 4th level. Okay, so this trim tree is actually doing this. What happens if I set this to 2? That everything goes back to one single branch, because what I'm doing, I am trimming the tree at this height. Of course, trimming the tree at this height doesn't mean that we lose the items, okay? But the items will be grouped on the remaining branches of the tree. So as the remaining branches of the tree is just this one, the main one, then all the data will be contained in the resulting branch, okay? So if you exceed by trimming the tree the number of sub-branching that you have, then you might incur in this kind of eventually undesired effect, because you are grouping all the data inside one single branch. Okay, so you're creating a list basically. But if you want to create a list, you might want to flatten the tree directly instead of working with trim tree. Okay, so let's leave this to 1 for now, and then we will go back to discussing this when we will talk about the shift path component. And then there is the unflattened tree, which is very interesting, because many times in Grasshopper, just in order to follow the way that some functions work, you need to flatten or graft or flatten things around the definition. And once you flatten a data set, which basically consists in a tree, you lose the information of the tree itself. So this unflattened tree, what it does is that if you, for example, let's take this tree here and let's copy it and let's flatten this tree. So now we know that we have one single list of values here. You might want to take a look, for example, at the path. You see that this only has one single index, so it's a simplified tree already. But what happens if I want to go back to the original tree? Why would I want to go back to the original tree? Well, basically, let's do something that might make sense. Let's say that I have this tree here, this list here that actually contain these values. And what I want to do, I want to add to any of the items that we see here, a string, for example, another chunk of text. So I would use a concatenate, which is one of the things that we didn't see because it's related to text handling. They are pretty straightforward commands, so that's why I prefer to use them instead of commenting them one by one. So concatenate, take a text fragment A and just append a fragment B to fragment A. So if I take a panel and just add a space, dash space, and then hello, and then I plug this here, what I am doing, let's copy paste this panel here. What I'm doing, I am appending this string to any of the items here. You see that nulls item are no longer nulls because the emptiness has been basically substituted by this string here. Okay, so there is no null items, but it's not a problem in this moment. We don't want to deal with null data. Okay, so I will just leave it like this, and let me move this a little lower. So now I have this different set of values, and I want to convert them into a tree, which is basically a tree that's able to interact with the first one. So it must have the exact same structure. So I will take these values that are coming from this list here, and as a guide, I'm going to use exactly the same structure of our initial data tree. Okay, like this. So if I take a look at the result, I see that each of the items has been placed inside one single inside one branch. So we have one item per branch, exactly the same structure that we had here. Okay, but without the hello. Okay, so this is the use of unflattened tree. It's very useful when you want to create a tree using the structure of another tree in order to have them available or ready for interaction. What do I mean by interaction? Well, any command in Grasshopper that generates a result, that produces a result starting from these two data sets here, is basically making these two trees interact with each other. Okay, so we will discuss this later on with practical examples. Okay, so this is the first group of commands in the tree group here in set toolbar. So you see that with trees, things necessarily become a little more complex because it's more complex to work with the data trees than with the lists. I am going to once again, as always, group these and eventually disable all these components here, and now we will go to the second column of functions. These are basically very simple data manipulation when working with trees. What I'm going to do, I'm going to copy them and move them here. So let's see what these things do. First of all, let's start with entwine. Entwine is something that is very useful to generate trees from different data flows in Grasshopper. So let's say, for example, that I have a list of values like this one, a series of values between 0 and 9, so 10 values. And I also have a, let's say, sequence of characters like this one. So from A to J, another 10 items, but this time is letters. And here they are. So what I want to do, I want to create a tree where one branch contains this data and another branch contains this data here. So I can use the entwine. Let me move things a little. I use the entwine and say the first branch will be this list here. The second branch will be this list here. I can add as many branches as I want. This is a dynamic component. If I get closer, you see that I have available 0, 2, but I can remove it because I only have two data streams here coming in. And as a result, what I get here is this. I have one first branch with numbers from 0 to 9 and another branch with letters from A to J. So basically what I am doing, I am creating a tree using different data streams as branches. And of course, you can also easily use a pattern viewer to see what's happening also in terms of graphical representation if you want. It's always very useful to work with pattern viewers when you're dealing with tree in order to have a clearer idea of what's happening. So if I, for example, parameterize the count here, so the amount of data that it's being created by the series and in the sequence, so I might have a branch with less values than the other one. Okay, as well as if I do the same with the char sequence. Okay, so we can easily understand what's the utility of this entwine. And entwine has flattened inputs. Now you see that this is not affecting the values, of course. This is affecting the path. So flattening means that in this case the tree will use the simplest path according to the values that are coming in. Okay, so for example, you see that if I change if I deactivate the flatten inputs, you see that the input name here changes. It's 0, 1. So you see that this means that the tree is grafted. And it's grafted because you see that the separation of the branches happens at the first index. And so you see, for example, that the graphic representation of the tree changes radically from these to these. Okay, so we have one additional level here. You see 1, 0, 0, but the branching happens at the first place. While if I flatten, I have just two levels, and branching happens at the second level. Also here we have the input here, 0, semicolon 0. This is something that you cannot change as you can do in basically all Grasshopper components, because this is automatically set by this method here. Okay, so it depends on what method you select for creating this tree. Yeah, basically that's pretty it. And explode tree is basically the opposite than entwining. So maybe we can, yes, we can use, for example, the same entwined tree here, plug it here in explode tree, and you see that explode tree just populates the output according to the amount of branches that are coming in inside the input tree. But actually it's not that important, that interesting here working with explode tree with this the result of this entwine. Maybe I would work with a more complex tree, which might be exactly the complex one that we had here. So it was this. So if I take this data tree here and plug it here, you see that first of all, the number of indices changes according to the structure of our tree. And our tree has a very complex structure because it has 18 branches, but there are two last indices are changing. Okay, why the explode tree is orange? Because it is saying that there are more branches in this tree than the two that we are visualizing here. So you see that this message here is saying the tree contains more branches than this component has output parameters. So we must add an output parameter to this object here, and we must fill the amount of branches if we want this error or warning to disappear. And you see that as soon as I get to 5.1, it becomes gray because it is saying that we are actually seeing all the available branches in this data tree. And of course, as a result, we have as an output the items inside each branch. This is because we have taken the complex version of our tree. But if we, for example, take this with just 5 branches, it contained the famous structure 2, 5, 2, 5, 2, 2 data inside. So if I take another data component and plug, for example, the chunks here, and temporarily enable this so I can internalize the tree here and then disable this again. So if I do this, you see that I have more output than branches here. So this explode tree doesn't automatically delete the redundant output, but here you see that, for example, in the available branches, you see that we have 2, 5, 2, 5, 2, and 2 data. Okay, so let me just delete all the redundant outputs and just let's use this this data tree here with less branches, so everything gets a little more clear. Okay, so this is what happens with the explode tree. Flip matrix. Now, flip matrix is a very important component. Actually, it's used in several design operations. We can only discuss the flip matrix for what it is in theoretical terms. So it's basically if you had experience of matrix algebra, then you might eventually recover what's the meaning of flipping a matrix. I am going to show you, for example, this with a small scheme. So I'm going to design a matrix, a very simple matrix, and this matrix will have 2 columns and will have 4 rows. Okay, so there will be 1, 2, 3, and 4, and 1 and 2. So what's the point in flipping the matrix? The point is that in Grasshopper, normally, whenever you get a component generating a tree of data, normally you have a matrix that is being read in columns. Okay, so data is ordered in columns. But for some application, you might want to read the data in lines. Okay, so if this is the case, you must switch from the original matrix that it's being read in columns, as the matrix will always be read in columns. You need another matrix that will be something like this. Instead of having 2 columns and 4 rows, we will have a matrix with 4 columns and 2 rows. Okay, so if we do this, it means that we are flipping the matrix, as you can see from the icon here, and we are able to read the matrix always in columns, but the data that we are reading is actually the data that is originally contained into the lines. Okay, so if we have, for example, here A, B, C, D, E, F, G, H, this matrix here will generate a reading as A, B, C, D, and then E, F, G, H. While if we read this, we will have AE, and then BF, and then CG, and then DH. So when we read it, we will have eventually this reading here. So it changes the way that we read the data inside the matrix, because it flips the matrix. Of course, this component can only work with rectangular matrix. So if we have a matrix that is not rectangular, then we cannot flip it. Okay, so let's take for example one of these situations here. So for example, if we create well, let's work with a geometrical component here, just because it generates a rectangular matrix. So if I go into vector rectangular grid, for example, this rectangular grid is actually generating a tree of cells. Okay, so each branch here contains a column of our grid, rectangular grid. So if I take, for example, extent y, which is the number of grid cells in base plane y direction, which is basically vertically, I change it to 1 to 5, set it to 1. You see that each branch contains just one cell, because vertically, mean in columns, we only have one cell per line, and we have 10 cells per each line. Okay, so this is becoming a single row of 10 cells horizontally. While if I do this, now I have 2 rows of cells. But as you can see, the matrix or the grid is not being read in rows. So there are not 2 branches with 10 rows each. There are 10 branches with 2 rows, with 2 cells each. So it means that the grid is being read in columns. And so if I take a param viewer, it means that this will be a data tree with 10 branches, each containing 2 values, which are the 2 cells. So this is the tree that we are seeing right now. I repeat, it's more useful to keep the param viewer in the text representation. So what happens if I flip the matrix? Now this is a rectangular matrix. Okay, no matter what I do with extent x and extent y, because I will always have a number an integer number of rows and an integer number of columns. Okay, so it will always be rectangular. So I can flip it, and if I flip it, what I have, it will be the same grid, absolutely the same grid, because I am not changing the values, I am changing the structure of the tree. But in this case, I will have 2 branches with 10 items each branch. So I always have 10 by 2, which are 20 cells. As you can see, we have 20 cells, 20 locally defined values here. And I will always have here 20 locally defined values, but they are grouped differently from the previous tree because the matrix has been flipped. So instead of having 10 by 2, I have 2 by 10. And so in this way, I can read the values or the items per row instead than per columns. Okay. We will see this in action in a practical exercise in a while. Okay. And then there is merging. Now, merging also is a dynamic component. It allows to receive several data streams, as many as you want. Okay, and what it does, it merges these data streams into just one. Now, this is when interaction starts to become important. Interaction between datasets start to become important. So if I take, for example, the same series and sequence that I had before. Okay, so I copy it here, and I'm going to disconnect the amount of the count. Okay, so I will disconnect the sliders, and what I want to do, I want to merge these with these. Now you see that as I fill the amount of inputs, the 3 appear automatically. Okay, so this is as far as I remember, is the only component that does this. Okay, so the moment you fill the inputs, a new one pops up in case you want to stream other cables or other data flows inside this merge component. So we already know what the series and sequence do. What we don't know is what does the merge to these values. And you can see that it simply creates a new list containing the first sequence or the first series from 0 to 9, and then appends the D2 flow, which is the sequence, the sequence of characters of letters from A to J. Now, this is partially true. Okay, so you must pay attention to this because if we take the panel here, we see that this series here is has a depth of 0, 0, so 2 indices for its path. And here we have 2 indices for the path. Okay, so basically what we are saying is that these two lists are being merged and the data contained in the two lists is at the same level. So that's why we have a new list with the same amount of indices for the path, and all the data is contained at this same level. What happens if we have lists acting or containing data at different depth for the path? Okay, so what happens, for example, let's see if we well, actually we can also use this command here. For example, if I take the sequence and I simplify the tree, well, actually this is not a tree, so I cannot do it, but we can take the let me see the trim tree. Okay, let's see if the trim tree works for this. Yeah, it works. Okay, because depth is set to 1 in this moment. Okay, so now we have exactly the same list of values, or the same items inside the list, but the depth is set to 0. Okay, so what happens if I plug this to here? You see that now, as the two lists reach a different depth, the path is made up of 1 index here and 2 here, they don't merge into one single data stream with the merge component. Okay, so we get once again a data tree. This is something that is very important, because this is not only important for the merge component, it's important whenever you have two lists or two data sets interacting between them. We will discuss interaction in a while, but it's absolutely more important than being able to graph and flatten trees. So in this case, for example, you see that we have a data tree, which it's also a weird data tree, because you can imagine, for example, that if I take a param viewer and take a look at these, I have two different depths, the same amount of items, two branches, but at two different depths. Okay, so if I do this, well, actually, I should work with several data flows. Let's see if I can do something tricky here. I will plug this into D3 and this into D4. Oh, of course, yeah, but they still merge because, yeah, actually, D3, D4 will have the same depth here. Eventually, I could take another one of these and set depth to 2. Let's see what happens, like this. Oh, there is not enough depth, of course, because this is a simple list. Well, actually, let's leave it like this. I was just creating to get to a more complex data tree here as a result, adding other lists with different paths, but actually it's not that important. We can do this easier. This can be done easier with the next components that we are going to handle here, but for now just leave it like this, and I hope the concept behind this is already clear enough. Okay, I just let me remind you that in case you have further doubts or you want to ask questions, you can also always send a message through the website or comment on this video here in my channel. So whatever works best for you, just get in touch and we will discuss these things further. Let's Ctrl G, Ctrl E, so let's switch everything off, and now let's go to the hard part of our tree analysis. Okay, so these 4 components here, let me copy them and let's move them here at the bottom. Okay, these 4 components here, things start to get juicy now, because these are quite important components. So match 3, for example. Match 3 always, because interaction between datasets is fundamental and we must control it properly. This match 3 is something that makes this interaction easier by taking one tree and matching its structure to another tree. For example, in this case, eventually we might want to use exactly these trees here. Let's see if we can do it. So for example, we have these two trees here, the original one and the grafted one. So I will take a data, copy paste it, and then I will have the original tree here and the grafted tree here. And these two, I will move them here. And internalize 1 and internalize 2. So let's disable them once again. Okay, so this is the tree that I want to match. This is the guide. So this is the simple tree. Just let's take a param viewer so we have a clearer idea of what we are doing. This time I will leave the graphic representation because of course with this kind of tree it's more evident with the graphical representation which is the complex one and which is the simple one. So what I want to do is take the simple one and match it to the complex one. Now you see that this is giving us an error because it says we need the same amount of path. Now in this case the two trees have a different amount of paths because they have the same amount of values, 18 here and 18 here, but they are distributed into different paths or branches, okay, because this is the grafting of this one. Okay, so what we can do, for example, is we have already seen we can trim this tree, and I would use the depth of 1 because I want to just delete the outer sub branching here and go back to our 5 branches. And now in this case, for example, I have 5 branches exactly like the first one. We can copy paste these. So when we use the match tree, we must have the same amount of branches, else this component will not work. Now, of course, in this moment, what I'm doing is basically it makes no sense at all because we are working with the same set of data. So the values inside these two data trees are exactly the same. So I am taking a data tree with 5 branches and a specific set of values and matching it to another data tree with the same set of branches and the same set of items inside. So there is absolutely no meaning in this. But later on, we will be able, for example, to create another data tree with a different set of items, and we can use this to work with this match tree properly, basically. And just remember that, let's switch back to the error. Just remember that what it's saying is that both the tree must share the equal number of paths. Okay, so in this case, it's not like, for example, like what we have done before, which was the sorry guys, which was unflattening the tree, because unflattening the tree can work with a list, not only with trees. Okay, we can take a list of values here and convert it into a tree using a guide, a structure. Okay, now in this case we cannot do it because this won't work unless the guide is also a list, but there is no point in doing this with lists. Okay, so this is only useful when you want to work with complex data structures like trees, of course. And now the path mapper. Path mapper is it was a useful component. I say it was because actually there are all these data manipulation utilities that we are studying here are capable of doing what the path mapper did before and more of what the path mapper was able to do. Okay, so I wouldn't get crazy using the path mapper. I will only show you what some of the potential of the path mapper, because it's actually the path mapper is not like a small scripting environment for data trees that you might want to use to customize the data structure according to your specific needs. So it's quite a complex command, the path mapper, but let's see what we have here. For example, let's go back to our rectangular grid, which is generating a tree of cells. Okay, just let's grab this and see what we have here. So we have 10 branches, each containing 5 values here. And it's important to use, for example, in this case, the param viewer with this text visualization, because we need to know exactly what's the path of the branches that we have. Let's say that I want to take this tree here, plug it into the path mapper, and what I want to do, I want to change the depth, for example, of these items. Okay, so I want to use the path mapper just to perform a simple operation, which is reducing the amount of indices in this path. So instead of having 0, 0, 0, 0, 0, 1, 0, 0, 2, I just want 0, 0, 0, 0, 1, 0, 2, and so on, eliminating one of the 3 columns. So let's double click on the path mapper. You see that this is basically the interface of the path mapper, and it's just when you see mapping in Grasshopper, it means that you are remapping something. So you must define the rule that takes the original set of values, or the original data, and transform this set of data into a new set. Now in this case, the set of data is not the items, is the path. Okay, so we can change the path from the source path to a target path. So for example, let's say that actually what we have here is curly bracket 0, semicolon 0, semicolon 0, and curly bracket closed. Okay, and if I take this, copy paste it, and eliminate one of the 3 indices and do this, this is the transformation or the mapping that I'm doing using the original tree structure. Okay, so if I copy paste the param viewer, and you see now that what I did is basically create one single branch with these 2 branches, with these 2 indices here, 0, 0. Now I don't want this. What I want is to take these, consider all the data that is not like this, all the varying index, which is this one, and I want to bring it to this. I am converting the changing index into a variable. So writing a here means that 0 and 0 stay constant in our structure, while the 3rd index is changing. So I give a letter to this index. And the path mapper in this moment knows that this is not a constant index, it's something that is changing through the branches. Okay, and what I want to do, I want to remap this path to this new path when we only have one constant index, and the corresponding changing index occupies the 2nd position. Okay, and I do this. And now we have a data tree with 10 branches, and I have reduced the amount of indices for the path. Okay, so this is one very simple use of the path mapper. Of course, there are many operations that we can do. For example, another operation. Let's leave this as it is. I would copy paste the path mapper, so I have 2 here. And what I want to do is create a mapping that produces exactly the same effect as the flip matrix. So you see that, for example, flip matrix is something that is way more practical than what we are about to do right now. I would say don't try this at home, but if you want to experiment with the path mapper, you are recommended to do this because it's very important. So the only thing that I would say is this. the original mapping that I have in the input data tree is that I have 0, 0, which is constant, that I have a changing index, which is A, and then I have the items, the amount of items, which is n equal 5. Now this I can represent it like with a parenthesis, I parenthesis. What I want to do right now is flip the matrix, flip the tree. So A represents, for example, the changing index of the path. We have 10 branches. Okay, so A ranges from 0 to 9. And then we have 5 items per branch. So I ranges from 0 to 4. Okay, so we will have 10 branches, each containing 5 items. What I want is a new data tree with 5 branches and 10 items. So what I will do is, if in case I want to maintain the same depth for the path, I would also add a semicolon 0. And then in this case, what I need to do is substitute the changing index with the amount of items. Because remember, when we flip the matrix, instead of having 10 branches with 5 items, we will have 5 items, so the items become the branches. So we will have 5 branches, each containing 10 items. So the branches becomes the items. Okay, so in this case, I would say 0, 0, I, and then parenthesis, A, parenthesis. Okay, so this is the equivalent of flipping matrix. And if we take a look at the result and do like this, we will have 5 branches, each containing 10 values, which is the flip matrix of the original data tree. So Path Mapper is a very powerful tool. Of course, you must practice a little with him. You might want to also notice that you can use these constants here: item count, path index. So instead of, in case you want to refer to the existing properties of the input tree, you have them available here. Okay, so just in case you want to experiment with this Path Mapper. Normally I no longer use the Path Mapper because the standard Grasshopper tools have become powerful enough to allow me to avoid scripting inside the Path Mapper. But it's interesting to experiment with it. Let me also turn off this graphical component here, or else you will have a preview coming out from this definition, and we don't want it. And now shift paths. Shift paths, remember that I was saying that it's something that looks quite similar to the trim tree. What I'm going to do, I'm going to take exactly the complex tree with 2 branchings happening. So I will take this. Let me move the split tree, and then I will take this and plug it into the shift path component. And you see that offset is by default is set to -1. So what is this shift paths doing is eliminating the last sub-branching. So it's offsetting the items from the last sub-branching to the previous branching available in the data structure. Of course, it depends on how many branching you have, how much branching you have inside your data tree, and how many sub branches you have. But if I take, for example, a slider between -2 to 0 and set it to 0, so say I don't want no offset, of course the data tree remains exactly the same. If I set this to -1, you see that the last branching disappears. If I set it to -2, all the branching disappeared because I go back to the trunk of our tree, and I get one single list with all the values available here as a list. Okay, so this is something like, as you can see, the behavior is very similar to trimming the tree using a depth. Because remember that the depth, take the other items as the surface of the tree. So depth means how deep you want to trim the branches of your tree. If you go depth 1, so you go deep 1 level, then you eliminate the outer branching down to 1 level, and then you go back to the level 2 sub branching. Okay, so here in this case is basically the same. You are taking the input data tree and you are offsetting who? Well, the items. Okay, and this represents, the offset represents the levels, how many levels you want to go down. Split tree is a tool that allows to break. Actually splitting a tree might be misleading. One might think, for example, that we are splitting the tree apart into separate sub trees, but actually what this split tree does is send to the positive output the branches that are identified by the masks that we input in this parameter here, and send all the other branches, the remaining branches, into the negative output. Okay, so building the masks is not so pleasant normally. We will discover later some tools that allow to do this automatically, but for this application I will just use a list item just to take the output of the param viewer, which are basically the masks that we are looking for. We have 18 branches in this tree, so I will set the index from 0 to 17 with a slider, and this will give us this output. So this is actually the first mask corresponding to the first branch, and I will plug this list item output to the masks. So you see that in this point, for example, the positive corresponds to asterisk A. So let's go back and see who is this asterisk A by plugging the original data tree to this new panel, and we see that this is actually the 00000, which corresponds to this mask. And if we take a look, so let's move this to here. So if we take a look at the negative output, we will see that the tree is no longer starting from asterisk A, it is starting from 0, 1, 2, 3, 4. So the first branch is sent to positive, and all the remaining branches are sent to negative. What happens if I set this to 1? 1 corresponds to 00001, which is the second branch in our tree, which corresponds to value 0. So the branch with value 0 is sent to positive, and all the remaining branches are sent to negative. So including the first branch of the original tree, and from the third branch on, you see that they are here. So we miss 00001 because it is sent to positive. Of course, we can take eventually several masks like this, and you will see that you can send to a specific branches of the tree to a separate set from the other one. If you want to work with split tree in the way that it's also depicted in this icon, which is basically taking the tree and splitting into two separate subtrees, the only thing that you must do is take as a masks. So in order to isolate all the interesting or relevant branches into the positive output, you must take all the masks that corresponds to the first branches of your tree, and leaving all the remaining branches to the negative output. So it's just a matter of building the proper masks that you must input into this parameter here in order to split the tree into two sub trees. Okay, so this is the split tree utility, which is something that eventually you might want to do in very particular occasion. I never use this in my regular Grasshopper workflow. So just to have an idea on how relevant or how common is to use this kind of tool in a normal workflow. Control G, Control E. Let's turn this third group off, and let's move on to these stream components here. So I will grab them, copy them, and move them down here. These are way simpler than the components that we have already seen right now. So these two commands here allow to merge two streams into one single output, or take one stream and basically subdivide it into separate streams via the gate option. So you see that you have, in this case, these are dynamic components, of course. If you get closer, you see that you can add or delete input streams or output streams. And the gate only allows to specify from which stream you want to read the output values. So for example, let's say that I take a series of numbers and a sequence of characters like this one. So I plug them here and here. So actually gate is set to 0. So I expect, for example, the output to be the numbers, and here they are. But of course, if I take a slider here from 0 to 1, I can change this to 1 and I will see letters. This is something that it might look, let's say, obvious and basically non-interesting, but it is not. Say, for example, first of all, you maybe you know that 0, 1 is actually it's like saying off, on, or false, true. Well, false true is actually the best way to interpret this 0, 1, especially if we work with two single streams and they are named 0 and 1, because if I take a Boolean toggle, actually the Boolean toggle it's emitting a false or true. But if you take a look at this, if you send this to an integer component, you see that the integer component is not getting angry or red or orange. It is able to understand what a value is coming in, and it is actually converting this value into 0 when the toggle is set to false, and into 1 when the toggle is set to true. So if I take this Boolean toggle and plug it into gate, you see that gate understands that when Boolean toggle is set to true, interprets this true as a 1 and pick the 1 stream. So we see the characters, and if I set it to false, we have the numbers. So when we are working only with two data streams as the input for the stream filter, you can use and name them as 0 and 1. Then you can use the a Boolean toggle. This is very important because in a workflow, when you use, for example, let's say loops, or like for example with anemone, you create loops, and then you can decide what is the exit condition for the loop by determining that if something happens during the loop, then a Boolean variable can be set to false. This is exactly the same thing that you can do here with the stream filter. If during a loop you want something to happen according to a true-false value, then you can do it with a stream filter. So in this way, you can send a true or false to the gate, depending on some other things that happened during the simulation, basically, the definition. And then you automatically can switch from one stream to another according to the true-false value that gets into the gate input. Okay, so this is something that it's very interesting when working with this stream filter. Of course, if I had here a stream number 2 and I select another series of numbers with a smaller count like this, and I plug this into 2, now there is no possibility for me to get to this third stream of data, because true false is not capable of doing this. But in that case, we can simply basically set the conditions so that gate can receive also the 0, 1, and 2 during the definition. Or we can use a manual control like this one, just simply increasing the slider to 2, and then I can send to the output the number series with 10 values, or the character series with 10 values, or the number series with 5 values, which is the stream number 2. Okay, so the important thing with the stream filter is not actually the possibility to stream several filters and then decide which one I want to have as an output, but it's automating the procedures so that the gate receive the index that we need in order to work with one of the input filters. So it's like creating an automatic gate definition inside our Grasshopper workflow. That's the interesting part of stream filter. And stream gate is actually the opposite. We can say that if we take, for example, let's say the series, and I plug it into the gate. Now, gate, as always, is an index that should vary according to the amount of outputs that we have here, and the name of the output that we have here. So it must receive 0 or 1 at the moment, and also remember that we can use a toggle. So if I set this to true, now the series is being sent to output number 1. If I set it to false, it is sent to output number 0. Of course, once again, the important thing is to define some automation inside the definition in order to have this gate defined automatically, and not being us, the one who double click on this Boolean toggle. Okay, I will leave a panel here to see what happens if we double click on this. And if we are not working with just two output streams, then we must use a slider, or provide this gate with values that depend on how many outputs we have here. Okay, so they are quite simple commands. Well, finally, let's take into account these last components, and also these ones. They are quite simple. We will take a comprehensive look at all of them. Eventually, starting from this one here, because I repeat, they are quite simple. Well, first, we have already saw that, for example, creating branches or masks when we need them is pretty boring, because we have to deal with curly brackets and semicolons and a defined amount of indices and so on. But in this case, for example, construct path can do the job for us automatically. So how does it work? It asks for indices as list. So let's take, for example, a panel, and let's type 0, enter 0, enter 0, enter 0, enter 1, for example. And now let's convert this. This is not a list of values, of numbers. This is a text, basically, with 1, 2, 3, 4, 5 lines of text. So if I say this is a multi-line data, Grasshopper converts this into a list of numbers, actually. So these are indices, integer numbers in a list. I will plug them here, and as a result, I will get a path, which is this one. Okay, so this is basically a path constructor, or a mask constructor, and it works automatically. And as there is a construct path, there is a deconstruct path. It just takes an existing branch or mask and converts it into a list of indices. So if I take, for example, the output of this branch and take a look at the output, I will have exactly the same indices. Just one consideration: always take a look at the amount of indices that form the path for one list. For example, this is a simple list with 1, 0, the unique index that we have here. And then after this process here, we have the same list of number, but with 2 indices here. Okay, so we are in a list which goes deeper into a tree structure. Okay, it's just one single list, but with a different path to get to the values. Okay, just consider this, because this might affect the way that data streams interact. For example, in commands that we have already taken into account, like, for example, this merging. Okay, Then there is this path compare. I will, for example, let's build a tree. In this case, I will build a, no, actually we already have a bunch of trees here. I will take a simple tree like this one, and I will use it, I will use it in order to understand how this path compare component works. I will use the paths from this data tree, which are basically the output of the param viewer. So here we have a bunch of paths. Now, don't worry about the fact that this component turns red. It gets angry, not because of the path that are coming in. They look perfectly fine. So if you take a look at the message here, there is no error with the input coming inside the path parameter. The problem is with mask. This is set to asterisk by default, which should mean something like whatever mask. Okay, so it's a wildcard, but you cannot use wildcards in this case. You must change this value to a path that corresponds to one of the existing paths here if you want this comparison to give you some true result. Okay, so for example, if I take, let's take a look at these paths here. I will take a panel, grab a panel, plug it here, and here we have the paths of our existing tree. Okay, so what I will do in this case, let's just play around with these components that we just saw. Okay, so just to have an idea of a little well, quite tricky operations that we are going to do right now, because they are totally useless, but just to have an idea of what we can do with them. I have branches here, so I can for example take a list item, take the first branch, which would be 0 0 0 0, and then I will deconstruct this path. So here I have the indices of this one, and then what I will do is basically substitute the last index of this path with a changing value. Okay, so for example, I will take let me move this a little further here. So basically I will go into the list and I will replace item. These are things that we already saw. So I will replace with the value that I want to substitute to this would be a number between 0 and 5. So I will take a slider between 0 and 5 and plug it here. And then I will say I want to replace the index number 3, which is the last index of our existing list. So I will take a panel with number 3 inside. Remember one important consideration: never give enter after writing a number if you want this to contain a number, this panel to contain a number, because if you do 3 enter, this is actually a text with 2 lines. Okay, so avoid hitting enter. And this is a panel with the number 3. And now we have 0 0 0 0. Let me grab a panel just so that we have an idea of what's happening. But if I change this, I have this changing index in position number 3. Okay, and I want to use this as a mask. Of course, a mask asks for a comparison mask. This is a list of indices. It is not actually a mask, but I will take a construct path, plug here my indices, and this converts into a path. So if I do this, now I have a list of paths coming in from the original tree and a reference path that can change according to this slider. And the result will be like this. We see that the first branch corresponds to the mask, so it gives us a true value, and all the remaining branches throw away false because they don't correspond to the mask that's coming in. And if I change this slider, I can detect which of the branches of my tree corresponds to the input mask of the path compare. Okay, Why this is important? Because, well, actually we can, for example, do something like deciding, for example, which of the branches of one tree we want to read inside the definition using this path compare. Okay, so this could be a very simple application of this path compare. Now, never mind this this huge construction that we did here. It was just to have the relevant values available inside our small definition. Normally you wouldn't do this, okay? But anyway, this is just to illustrate how this path compare works. And then there is replace paths. Now, data is the tree that we want to work with. So I will take the very same tree that we have here. So my tree will be actually this. And also let me move this down a little so I can make room a little here in this definition. So here we have the information of this tree, the structure. Here we have the information of the values inside this this data tree, just to have an idea of what's the content of the data streaming inside the data input. So search and replace. This is actually a double input, which are basically masks, as you can see. So search for a text, which is actually a mask, and replace with a branch. See this black icon. This black icon is set into the params primitive. It's not a geometric primitive, of course. It's a non-geometrical primitive. It's data path. Okay, so you see that this is the icon that we see here in this kind of component. So, for example, what I want to do is search for a mask. Now, the mask could be, for example, one of these. So let's grab a list item and consider, for example, the first one. This would be the branch that I want to replace, the path that I want to replace, and I want to replace it with another list item, but with index set to, for example, 0 to 5. Oops, sorry, 0 to 5. So basically what I'm doing is retrieving any of the branches of the original tree and use it in order to perform a useless substitution, because I will replace the first branch with the first branch in this case if I plug this here. Okay, so if I take a look at the result, in this moment I am doing absolutely nothing. The tree remains exactly the same because I am replacing the first branch, which is this item here deriving from index number 0, and I am replacing with index number 0 once again with the same branch. Okay, but if I change this to 1, I am replacing the first branch, which was asterisk A0, with the second branch. So you see that I have asterisk A0, 1, 2, 3, 4, asterisk B. Okay, so I am replacing the first branch with the second one. Okay, and if I do something like 2, you see that now we have first branch becomes 1, 2, 3, 4 asterisk B. Okay, and then we have asterisk A0, 5, 6, that becomes the second branch. Okay, so I decide what branch I want to replace in this tree, and you see that it simply flows across this the data tree. Okay, so that's how replace path work. Of course, you can. This is also, once again, just don't think about this in terms of a real life scenario or a real life application. It is basically useless. Eventually in the exercise session we will build a specific geometric scenario in order to see the use of these replace paths in a real situation, in a real context. Okay, so Control G, Control E for this, and now let's go and analyze these 4 components here, which are a little more complex in terms of how they work, but and also I must be honest, I never use them in my regular workflows in Grasshopper. But anyway, what do these components do is retrieving items inside a tree, a data tree. So you see that we have relative items and relative items working with one tree or two trees, and then we have tree branch in order to retrieve a particular branch from a tree, which is pretty simple. And then we have tree item that allows to retrieve a specific item from a data tree. Okay, so these two are quite simple. Let's take a look at these retrieve items. They work basically the same, but they work with one or two trees. You see that all of these components here have a wrap, well, not tree branch, but the tree item, yes, has a wrap, and then relative item and items have wrap paths and wrap items. Okay, so wrapping is something that maybe you already know. If you take a list item, for example, there is this wrap. If you take a shift list, there is wrap. Okay, so what is this wrapping? Let's let's consider these two components. It's easier to understand with this. So I will write down something like this. So imagine this is a list containing these values 1, 2, 3, and 4. So we know that the value 1 has index number 0. This has index number 1, 2, and 3. Okay, so these are the indices and these are the values. Okay. What happens, for example, when I use a list item? The index is an integer number that should range between the lowest index and the highest index. So if I set this index to 0, ranging up to 3, there is no problem for list item to identify the values 1, 2, 3, or 4. What happens if I provide an index like 4? We don't have index number 4 in this case. But if wrap is on or is true, then Grasshopper would simply take all the indices 0, 1, 2, 3, and when we give 4 as an input to the index, it will go back to the first index and consider it like the fourth one. And so this is also becoming 5, 6, 7, 8, 9, 10, 11, and so on. So when wrapping is on, even if you exceed the value of the highest index that you have inside one list or one tree when you work with paths, then Grasshopper will go back and start again from the first index or the first path in order to retrieve the desired data. Okay, so that's the meaning of wrapping, and we see that wrapping actually refers both to paths and items. Of course, to paths as well, because if we have a tree with branch number 0, 1, 2, 3, 4, for example, and we want to retrieve branch number 6, then we have, this is branch number 0, 1, 2, 3, and 4. But if you want the path with the 6, then Grasshopper will consider this as 5 and this as 6. So this will be the branch number 6. And inside each of these branches, you have a list of items with the indices, for example. And if you use an index, like for example 6 once again, then this will be item number 6. Okay, so this wrapping affects both paths and items inside a data tree. Now, let's, for example, take a simple tree, like let's create a series, and let's graph this in order to have this. We already know what this tree look like, so it's just numbers from 0 to 9 into 10 separate branches. Okay, it would be interesting here to have a param viewer set to a graphic representation, just to have a quick look at how this relative item is working. And I will also take this and plug one to item A and one to item B, just to have an idea of how this tree is going to change. Now, it asks for offset. Offset is not actually in this comment, it's not a number, okay? It's a text. So once again, remember that when you work with data trees, basically most of the time you will be working with paths or masks, okay? So this is actually asking for a mask. We must know what is the aspect of the mask for our original tree, which is 0, 0, 0. So we have 3 indices, the last one is changing, okay? Only the last one. So if we want to retrieve relative items from this tree, you must use one of these, you must use this masking here. So if I take, for example, like 0, okay, like this, 0 enter 0, and say this is a multi-line data, okay? So we have this, and then I grab we have 10 branches here, so 0 to 9, and just to perform just a little data manipulation here, I will take a data container and plug the list with this here, okay? So here, as a result, we have these 3 values. I plugged first the panel and then the slider, so the slider is actually occupying the last position. So if I increase this value, you see that the last value is changing. And now that I have this, I will use this set tree construct path. So I will have this as converted into a branch. So if I do this, now I am telling Grasshopper I want to retrieve item using this mask here. Now, what happens with this? Well, actually, nothing happens in this case because I am using exactly the same first branch, so there is no offset basically starting from the extreme left or right of the tree. There is no offset because I am using the first branch. But if I set this to 1, you see that now, for example, the number of branches here has become smaller, okay? So what's happening here? We must take a panel in order to understand what's happening with this tree here. So I will take this, and you see that when I use, for example, offset using 0, 0, 1, then you see that I have the values here are 0, 1, 2, 3, 4, 5, 6, 7, and 8. We missed the last one. Okay, but here in the other tree, we don't start from 0. We start from 1 and reach 9. So what's happening here? What's happening is that this relative item is eliminating the outer trees. Okay, so we are basically saying I don't want to take into account in this tree here, starting from the last one, I don't want to take into account the last item or the last branch, and here I don't want to take into account the first one. Okay, so you see that, for example, if I remain here on the last branches of the tree and here on the first branches of the tree, if I increase this, you see that 8 and 9 disappeared and 0 and 1 disappeared from this. Okay, so if I increase, you see that here I am missing the remaining branch at the end of the tree. I only maintain the 0, 1, and 2, which are the first 3. And here I have the last 3 items or branches of the tree. Okay, so this is how relative item works. Of course, what happens if I get to 9? If I get to 9, I have exactly the first branch and the last branch. But if I increase this to, let's say, 39, and then I do this, I am exceeding the number of branches that I have in my tree. Okay, so wrap paths is set to false. If I take a Boolean toggle and set this to true, now what I am doing, I am going back to consider this not only the amount of branches that I have, but I am cycling over and over inside the data tree structure inside the branches. Okay, So this is what happens when we activate a wrap inside these components here. We can exceed the amount of values, but it becomes a little more difficult to understand what we do if we activate the wrap paths in this case. Okay, so I would recommend that you eventually use the same amount of the same range of values as the branches that you have in your tree. Of course, this is not always possible because you might have changing data structure inside your definition in terms of how many branches you have inside your tree. So you cannot easily understand how to create this branch, this mask here. Okay, so it's not always possible to do this, or it's not always easy, but yes, you can always find a way to do this. Okay. Okay, so let's switch to relative items. This is actually basically the same. I will take this series. As always, when I work with two data trees, I will take also a sequence. They are basically, they have a similar structure. So if I graph them, I will have two trees with 10 branches exactly identical in terms of structure, data structure. Okay. So I will use the numbers as tree 1, tree A, and the letters as tree B. Okay. And then I need an offset. I will use the same offset that I have here, so just don't waste more time in this. And I will copy paste these trees with panels. So I will do like this, and I will do like this. Okay, so you see that in this case it is working exactly the same, but item A refers to tree A and item B refers to tree B. Okay, so what happens is that here I will have, according to the offset that I am using, I will have only, for example, out of 10 branches, I am offsetting by 7, so I only have first 3 branches and the last 3 branches of the original trees that I am considering. So it's pretty straightforward once we know how the retrieve item works. We are only working with 2 trees. So item A refers to tree A and item B to tree B, but the behavior is absolutely the same. It's also the wrapping works exactly the same. Tree branch is pretty obvious. Now if I take, for example, the number 3 and plug it into tree, I want to retrieve a specific branch inside belonging to this tree. I need a path or a mask. Okay, so what I will do is, well, we already did something like this. I will take this list item, for example, apply it to this param viewer. You know that param viewer outputs the list of masks, each well, not masks, but paths, each belonging to each branch of the tree. So list item is actually giving the path to the first branch. Okay, so 0, 0, 0. And what I will do is take this and deconstruct the path just to have the list of indices, and then I will replace items in this list. I will replace with a slider between 0 and 9, the index number 2, which is the last index that we have in our list. Okay, so 0, 1, and 2 is the last 0. So what I'm doing here, I am building a new path that can change. Oops, sorry. Yeah, it needs a path, not a list of number. So I need to build once again, to construct once again a path, and then I can feed this tree branch. So what I'm doing here is, we already know it, is build a variable branch like this, according to the number slider. Okay, like this. And so if I take a look at what's coming out from this is actually the content of the branch that I am selecting using this tree branch. Okay, so this is the way that this tree branch works. Of course, I repeat, this is absolutely useless you have to deal with real-life scenarios. This is not a real-life scenario. It's just to understand how this tree branch work. And there is also a maintain paths option here, which is pretty important. You see that the list of items that represents the content of this branch is actually maintaining the path, okay? So 002 is actually exactly the path that we are using to retrieve this tree branch. If you don't want to maintain this path, then you will have a simple list with one single index. So it's a simpler list in this case, okay? It depends on the use that you want to give to the output of this component. And so we have ended the analysis of this set toolbar. So we have finished the analysis of all these lists and sets and tree components. Now what's next? We will start doing some practical exercises in order to better understand how this component work in a standard Grasshopper workflow, and how we can use them in order to solve precise problems that might occur during the scripting, the visual scripting workflow. So let's switch to the exercises.